Hi students, let us see in this video about controllers. So we will discuss proportional controller and proportional derivative controller, that is like P controllers and PD controllers. So let us see the importance of using these controllers in the control systems. Let us see the prerequisites. Okay, you should know open loop and closed loop transfer functions, and you should know the time response of a system, especially how to find the value of zeta, that is damping factor, and the oscillating frequency omega n. Of course, these usual things. Okay, now let us start with the analysis. Let us consider a system having a controller. So this is a controller, and this is the actual plant what we have. So this is a plant having some transfer function, and assume that this is in a unity feedback system. This is minus, this is RFS, this is CFS. So this is the system what I have. I have a controller. So there is a system or a plant having some transfer function. So I want to see the impact of this controller on the overall response of the system. So now let us start with a transfer function whose GFS is something like 10 by S plus 2 and S plus 4. So this is the plant what we are having a transfer function this, and we are having HFS as 1. So let us not consider the controller for the time being. So let us consider this block is represented by 1, meaning there is no controller in place. So let us try to find what are the time responses and steady state error of this particular system. If we can see now, GFS of this system is 10 by S plus 2 into S plus 4, and similarly, since HFS is equal to 1, so GFS into HFS happens to be 10 divided by maybe S square plus 6S plus 8 is my open loop transfer function. This is open loop transfer function. So we know that closed loop transfer function is given by GFS by 1 plus GFS into HFS. So if I substitute GFS and HFS onto this, so this becomes 10 by A square plus 6S plus 8 divided by 1 plus 10 by, this is 10 by A square plus 6S plus 8. So from which I can write upon simplifying the CFS by RFS, which is nothing but the closed loop transfer function is now given by 10 by A square plus 6S plus 18. So this is the transfer function. So for this transfer function, if I equate the denominator to the standard second order system characteristic equation, of course we know that if you equate the denominator to 0, this will become the characteristic equation. The general characteristic equation of a second order system is A square plus 2 zeta omega ns plus omega n square equal to 0. By equating this, so we can write omega n for the corresponding system is under root of 18, and zeta is given by 6 by 2 into root of 18. So let us try to find out these values of omega n and zeta. So omega n happens to be root of 18, which is 4.24 radian per second, and this happens to be of course into 2, 1 over that into 6. So it is now 0.707. So this is the value of damping ratio and the natural undamped natural frequency. So for these values, let us try to find out what is the maximum overshoot for a step input. If I consider R of S, which is equal to 1 over S, which corresponds to a R of T of U of T, that is unit step function. For a unit step function, we know that expression for MP is given by e power minus zeta pi divided by under root of 1 minus zeta square. Now for this system having this value of zeta, for a unit step input, I want to find what is the response. Meaning for this system, if I'm applying a unit step input, so I know that I'll be getting a response something like this, because it's a second order system. I'll end up with something like this. So this is the response I'm going to get. So we are now interested in what is this MP, and suppose if you're considering a 2% settling time, so of course 1.02, or this is 1.02, this is 0.98, corresponds to 2% settling time, 2% settling time. So we are trying to find out what is TFS for 2%. This is the expression for MP, and similarly we have the expression for TS for 2%, which happens to be 4 by zeta into omega n. Since we know the values of zeta omega n, we can estimate what is TS and MP for this particular system, for this system. So let me just find out now. So this happens to be, of course, settling time happens to be 4 divided by zeta is 0.707 and omega n is 4.24. If I do this, this happens to be 1.33 second. So this is my settling time. So let me find out how much is MP. So MP happens to be, so how much is that? It is e power minus of zeta is 0.707 into pi divided by under root of course divided by under root of 1 minus 0.707 whole square, close. Okay, now you can see the MP value coming out to be 0.0432, that is 4.32% overshoot. So this is the MP value. Okay, let me just write a table here. So in this table, what I'm going to list is, so this is a comparison table to see what is the effect of a proportional control and derivative control for the given system. So I will consider now, so this is the controller, so assume that we are starting with proportional controller. So now what is the value of Kp that you are having, that is that the compensation, this block, this controller, are you having some value or not? Okay, now that is what is this. Next is, so we are trying to find out what is the value of MP and what is the settling time, and also let us try to find out what is the steady state error if I apply a step input, So these are the parameters we are supposed to find out. So first we are starting with, of course there are no controllers, so controller is not applied, so we don't have a value of Kp. Now Kp is 1, so for that Kp of 1, so for a GFS into HFS, which is equal to what we have, so we actually have it as what is that, 2 and 4. So we have it as 2 and 4, which is 10 by s plus 2 into s plus 4. For this particular transfer function, MP is coming out to be 4.32%, and what is the value of TS? TS is actually 1.33 second. This is in second, of course this is in percentage. Let us also know what is ESS. So ESS, we know that steady state error for a step input is given by, So ESS is actually given by 1 over 1 plus Kp for a unit step input. So we know that Kp is nothing but limit of S tending to 0 GFS into HFS. So we already have the GFS into HFS, which is this. So now let me substitute that 10 by, so S square plus 6S plus 8 is my GFS into HFS. You apply the limit of S tending to 0. Can you see now, does this become 10 by 8 is my Kp value. Suppose if you put it here, so it is now 1 over 1 plus 10 by 8, which happens to be 8 by 18. Suppose if you take this 8 by 18, so it is 8 by 18 is 0.44. So this is the ESS value. So this is the ESS value. So let me just put it here. This is 0.44. This is without having any controller. So no controller is used. So we took the value of Kp so and so. Now let us consider a controller. So this is now, let me have a controller whose value is 10. So now what we are doing is, when you have a controller with Kp is equal to 10, so of course don't get confused with this Kp, this is different. This Kp, if it is 10, okay, let me just write it as some Kp dash. This is Kp dash, which is the proportional controller value, which is now 10. So what will be the transfer function? So does the transfer function now becomes Kp dash, so now this is Kp dash into 10 by S square plus 6S plus 8. So what is this Kp dash we are assuming? We are assuming it to be 10. Can you see now, does this is my GFS into HFS after including this Kp dash of 10 of 10. So since they are in series, you are supposed to multiply this with this. So upon multiplying, can you see now, is your GFS into HFS is equal to 100 by S square plus 6S plus 8. Then what is its CFS by RFS? Its CFS by RFS is naturally equal to 100 by, so it is S square plus 6S plus 108. So only thing is that this constant term what you have will be added with 100. So now let us find out what is omega n and zeta. So omega n is under root of 108, it is under root of 108, sorry, so which is 10.39 radian per second. Zeta is actually 6 by 2 into 10.39, so it is this into 2, 1 over that into 6, so it's actually 0.288. Now you can see, the moment you added this controller with the value of k is equal to 10, the damping ratio has changed, and of course naturally the natural frequency has also changed. So this will have an impact on MP. So what is MP now? It's e power minus zeta pi divided by 1 minus zeta square. And what is that value? Let us also find what is Ts, which is nothing but 4 by zeta omega n. So we have the value of, let me find this first. Is it not 4 divided by 0.288 into 10.39? So now the time is 1.33 second. Let us find what is MPs. So maximum O shoot now is e power minus 288 multiplied by pi divided by under root of 1 minus 0.288 square. Close. You can see now it is 0.388. So when you have a value of Kp is equal to 10, MP happens to be 0.388 and Ts is this much. Let us also find what is ESS. So ESS is equal to 1 over 1 plus Kp. So Kp is now this value. So this is my GFS into HFS. Is it not 100 by 108. So what is this? This is like, okay, 108 by 108 by 208. 108 by 208. So what is 108 by 208? You can see it is 0. Sorry, it's not okay. Just a minute. It's not 108 by 208. This is 100, and this will become, this is GFS into HFS. This is actually 8. So is it not 8 by 108? Is it not 8 by 108? So what is 8 by 108? 8 by 108 is 0.074. So let us tabulate this over here. When you had a controller with Kp dash is equal to 10, sorry, this controller, proportional control is there, Kp dash is now 10. What is MP? So MP has risen from 4.32% to 38.8% is the overshoot. So settling time is almost the same. It is again 1.33, but you can see ESS, the steady state error, has reduced to 0.074. So what we want to see here is, when you use a controller with P is equal to 10 or Kp dash is equal to 10, a proportional controller, overshoot increases, settling time remains the constant, but the steady state error has reduced. Maybe you can try this for a different value of Kp. So maybe you can just try it for 25, see what happens to this. Maybe you can also try it out for 0.5. So reduce, this is again, you take it as P controller, take this Kp dash as 25 and take it as 0.5. Try to see this. Of course, you just find out what is MP, TS and ESS. You will get to know what is happening to your ESS. So it is surprising to see, as the value of this proportional controller increases, the overshoot also increases, the settling time almost remains constant. This ESS will reduce, the steady state error will reduce. So let me just try to find it out for 0.5 as a value of Kp dash. So now shall I just do it here? So for a value of Kp dash is equal to 0.5, can you see now, does this become 5 by s square plus 6s plus 8? This is my GFS into HFS. What is my CFS bar Fs? Will it not become 5 by s square plus 6s plus 13? So what is zeta now? Zeta happens to be, okay, omega n is under root of 13, which is 3 point, omega n is 3.6. Zeta happens to be 6 divided by 2 into 3.6, which happens to be 0.833. So with this 3.6 and so on, so it is now 4 divided by 3.6 into 0.833. This is my TS. So TS happens to be same. TS is 1.33. So I can write this as 1.33. So let me try to find out what is MP. So with this, zeta is 0.833. So it is exponential minus 0.833 into pi divided by under root of 1 minus 0.833 square, close. Can you see now it is so small? So MP happens to be, of course, let me make it into 100. Can you see it is 0.882%? So it has reduced to a great extent. It is now 0.882%. So percent itself is this much. It's not 88%. It is 0.882%. Let us find out what is ESS. So what is ESS? ESS now becomes, can you see now, is it not 8 by 6? So this will become 0. Now for this, is it not, okay, 1 over 1 plus 5 by 8. 5 by 8 is actually equal to, okay, this is fine, this is 8, this 8 will go there, so this will become 13. So now when it is 13, so now it is 8 by 13. 8 by 13 is 0.615. So it is now 0.615. Just compare no compensator, of course no controller. You have a controller with Kp which is less than 1. Can you see the overshoot has reduced? Overshoot has reduced. The settling time remains almost the constant, but you can see ESS is more. The steady state error is more if the value of proportional controller is less than 1. If it is more than 1, you can see ESS reduces. So ESS reduces, but MP will increase if I increase the value of Kp dash. How about TS? TS almost remains constant. So this is a summary of proportional controller. This is proportional controller. In case of proportional controller, if you increase the value of Kp dash, that is the proportional constant value, steady state error will reduce, but overshoot will increase. Overshoot will increase. The settling time almost remains constant. Almost remains constant. Is that fine? So this is how it is happening. Now, after seeing this proportional controller, let us see how does a proportional and derivative controller will have an impact on this. So now, what is a controller? So controller is not simply that constant value. So it is having some constant value K. Along with that, I will have tau into S as one more parameter, which is indicating the derivative part of that PD controller. So this is now we are talking about PD controller. So this is derivative controller, which is tau into S, and this is my proportional controller. So I have a summing point. This is plus, this is again plus here, this is added, and we still have the same controller, which is now we took it as 10 by S plus 2 and S plus 4. This is this. Let me have a unity feedback. So this is RFS, this is CFS. So now let us take the value of K as 10. Let us take the value of tau as 0.1. If I take this as 10 and this as 0.1, so does this block represent 10 plus 0.1? Yes. Is that coming in series with this? 10 by S square plus 6S plus 8. Is this my GFS into HFS? This is my GFS into HFS by including a proportional controller and a derivative controller. Now you can see they are coming in parallel. So that's why it is plus, and this parallel combination is coming in series with this. So that's why it is into. That's why it is into. Now for this, let me find out what is, can I write it as 100 plus S divided by S square plus 6S plus 8. This is my open loop transfer function. If this is open loop transfer function, so how does its CFS by RFS will look like? CFS by RFS will look like what? Is it not 100 plus S divided by, can you see now it is S square plus 6S plus 8 plus 100 plus S. Is this not equal to 100 plus S divided by, is it not s square plus 7s plus 108. This is my transfer function. So is this my what is this? This is my characteristic equation. I can equate this to s square plus c2 zeta omega ns plus omega n square, from which I can know the value of omega n and zeta. So what is omega n now? For this PD controller transfer function, so including PD controller, what is the overall closed loop transfer function is this? So is this not equal to 108, and is this not equal to 7 by 2 into under root of 108? So what is this 108? Under root of 108 happens to be 10.39 radian per second. How about this? This is, of course, that into 2, 1 over that into 7. So is my zeta is equal to 0.336. So for the same plant whatever we had, now we are trying to have a PD controller with this as 10 and this as 0.1, yes, 0.1s. So that coming out to be this much. So what is GFS? So GFS is actually this much. So GFS into HFS is actually now, of course you can just write it as this is 100 plus s divided by s square plus 6s plus 8. So I want to find what is Kp. So Kp is nothing but limit of s tending to 0. So in this, if you make s, in this particular thing, if you make s tending to 0, is it not 100 by 8? Is it not 100 by 8? So Kp is equal to 100 by 8. What is ESS then? Is ESS equal to 1 over 1 plus Kp? So is it not 1 over 1 plus 100 by 8? So what is this now? Is it not 8 by 108, which is 0.074? So now we have a PD controller. You can see now we have a PD controller with this as 10, with this as 10. Let us try to find out how much is MP. So we have this as my zeta value. So how to find out now? It is exponential minus of 0.336 into pi divided by under root of 1 minus 0.336 whole square, close. Can you see it is 32%? So it is now 32.6%. How about this time? This time is now okay, settling time is nothing but 4 divided by z time to omega n. So zeta is 0.336, omega n is 10.39. So it is coming out to be 1.14 second. How much is ESS? ESS is 0.074. Now you can just compare these two now. This is P controller, this is, okay, let me just say this. With this PD controller with K as 100, let me also write its corresponding tau. Tau is 0.1. If tau is 0.1, I have an MP of 32%. See here? So there is a slight reduction in the value of MP compared to proportional controller, that has slightly reduced. Can you see this is taking 1.33 second, now it is taking bit lesser time. It is taking bit lesser time to settle to 2% tolerance. Can you see ESS is almost same? So this will keep the ESS same, the steady state error remains same, but it will improve the overshoot from 38 to 36, sorry, from 38 to 32. The settling time reduces from 1.33 to 1.41. So there is a good response if you have a PD controller with the same value of Kp, and of course this is tau is equal to 0.1. If you change the value of tau on this will certainly change. But what we are trying to understand is, in case of okay, now if you compare PD controller with no controller, PD controller with no controller, can you see this is certainly increased? So this is comparing to without controller. So if you can consider, okay, compare the PD controller with no controller, so if you increase, this is K and tau value. If the value of K and tau, of course we cannot just say increase or decrease. Can you see ESS has certainly reduced for a given value of Kp and tau? Can you see this settling time also has reduced? Of course, there is an increase in the value of MP. So you could able to get a better response in terms of settling time and the final steady state at the cost of overshoot. Maybe you can change this value of tau to 0.05 and again verify what is this MP, TS, and okay, let me just do that. PD, let me just take it as 10 only. Let us take tau as 0.05. Suppose if I reduce the time constant further, what is the impact of that on the overall response? So how does that going to reflect here? This will going to reflect here. So can you see now this will become 0.05. When this is 0.05, so what is 10 into 0.05? So that happens to be 10 into 0.05 is 0.5 yes. So what do we have? We have GFS into HFS is now equal to 10 plus 0.05 yes into, this is my old transfer function, s square plus 6s plus 8. So then this becomes 100 plus 0.5 s divided by s square plus 6s plus 8. This is my GFS into HFS, and then of course this will not change my, you can see there is no change. The denominator means okay, this ESS remains 0.074 even if you change this to 0.05, that is very evident. But let us see what is CFS by RFS of this. So CFS by RFS becomes, so is it not okay, now this remains same, 100 plus 0.5 s. So now what will be this? Is it not s square plus 6.5 s plus 6.5 s plus, so this will become 8, no it is 108. Can you see now this is the change? Here this was becoming 7 by so and so. Now the zeta value slightly reduces. So what is zeta now? Because omega n is remaining the same, because you had 108 here, you had 108. So now the change that is happening here is 100 plus 0.5 s divided by s square plus 6.5 s plus 108. So this will not change your omega n, so omega n remains the same. This zeta will change, so this zeta will change to 6.5 divided by 2 into under root of 108, so that happens to be, of course this changes to 0.312, a very small change. So this will certainly have an impact on the overshoot. So now what is the overshoot? So for exponential minus of 0.312 multiplied by pi divided by under root of 1 minus 0.312 square, close. Can you see it is now 35.6% is the overshoot, slightly increased because the value of zeta has reduced, means MP has to increase. Let us find out what is this. So since this has reduced, this will slightly increase. Now that is settling time. So is it not 4 divided by 10.39 multiplied by multiplied by the zeta value. Zeta value is now 0.312. Can you see it is 1.23? This is the result. So same PD controller, if I retain the value of proportional value is 10, and if I increase the time, reduce the time constant from 0.1 to 0.05, the overshoot slightly increases. This will also increase, and ESS almost remains constant. ESS almost remains constant. So now in this PD controller, keeping this KP constant, if you increase or if you reduce tau SS, if you reduce tau of S, so KP value will actually, this is not KP, the MP will increase, the TS will also increase. You can see compared to these two, TS has increased, and ESS remains constant, ESS. So what I am trying to do is, among PD controllers, if you reduce the value of tau, the overshoot will increase, that settling time will also increase, but this remains constant. But if you compare this PD and no controller, you still have an advantage. You can see from 1.33 it is reduced to 1.23, from 0.44 it reduces to 0.074, and of course there is an increase in the overshoot from 4.32 to 35.6. So this way we can able to see the impact of this controller, without controller, and within this PD controller. If you change the value of tau, keeping the value of K. You can try the other way, keep this as a 0.1, change this from 10 to 50 or 10 to 25, see what is the impact of that. So that will be a good exercise for you to understand the impact of each P and D values, or the time constant of this derivative, how it is going to change. Okay, in the next video we will see PI controller and PID controller. So PI controller stands for proportional and integral controller, whereas PID is proportional, integral and derivative. All the three effects will be there. Thank you.